Okay, recording is now going. Micromechanical strength theory. Boy, that's terrible handwriting. You think I'd be getting better at using this writing pad, but really, I'm not. It's difficult. Okay, we get it. Presidents are momentary. Pultrusion is forever. Agreed. Okay, so micromechanical strength theory. Let's get into it. So far, we've really just talked about sort of strength or stiffness and compliance, but let's now start talking about strength. And strength is obviously like stress to failure, and just like material properties, elastic modulus, shear modulus, etc., we also have orthotropic behavior for strength. You're going to have different strengths in different directions, so we need to be able to sort of tackle that and talk about that. Okay, so I'll just say that here. Like other composite properties, strength is orthotropic. I'll just say anisotropic. A little bit more precise. Okay, so it sort of depends on the orientation of loading. Like with respect to material axes, if you want to think about a fiber direction and the loading relative to like a fiber direction. Okay, and even in like what is the most simplistic composite, which we think of like a unidirectional composite is like the most simplistic, it's really complicated. Okay, so even in simplest composite, which is like a unidirectional composite, very complicated. Okay, and that's because you have like multiple materials that each have their own failure strengths. You have stress concentrations that come from fibers, and you could possibly be loading in a variety of different directions where stiffnesses and ultimate strengths are different. Man, complicated, okay? So depends on many things. And I'm just going to list a few here. This is not really an exhaustive list, but it's going to depend on a lot of things, including strength of fibers, strength of matrix, obviously. It'll depend on the bond between the two, that interface. So I'll just say interface or interfacial bond. Bond, interfacial bond. All right, it could depend on like surface roughness or surface flaws. This is more of a sort of a fracture mechanics theory, but kind of rears its head in strength theory as well. Could depend on voids, if you have voids on the inside. Could depend on previous damage, like if you have any previous plasticity, that could also affect. I'll just say previous damage. So if, like, let's say you have a composite and there was a bird strike, now you have a bunch of damage on your composite, your strength is not going to be nearly what it once was, right? So obviously that's going to be important. So previous damage. All right. What we're going to do over the next, I don't know, 3 or so lectures is talk about the strengths in the principal coordinates, principal material coordinates of a unidirectional composite. So to start, we will discuss models of strength in principal material coordinates of a unidirectional composite. Okay. So like obviously kind of the picture that you want to have in your head is sort of the traditional picture of a unidirectional composite. Just something like this, where we sort of have fibers that are sort of running all along this direction. Our continuous fibers kind of running in this direction here. And so our coordinate system would be like something like 1, 2, 3. That looks like the following. So when I say we're going to talk about failure in the principal directions, we're going to talk about tensile failure in 1, compressive failure in 1, tensile failure in 2 and 3, which is the same, compressive failure in 2 and 3, which is the same, and also shear failure 1, 2. All right, so we got a lot of things to sort of talk about. So we'll cover longitudinal tension. Oh my gosh, longitudinal tensile failure. So this is like tension in the one direction. This is one axis. We'll cover transverse tension. So this is like the 2 and 3 axes. Remember, it's sort of a plane of isotropy, that 2-3 plane. Longitudinal compression. So that would be, again, like the one axis, but here in compression. We'll cover transverse compression. Which is, again, the 2-3 axis. Maybe you want to call it the 2-3 plane, since it's, kind of all isotropic. And then finally, we're going to cover transverse shear failure. Which will be like the 1-2 plane. All right. Some of these are easy. Some of these are difficult, lemon difficult. Okay. The ones that are easy are going to be transverse tensile failure, transverse compression. And why do we think those are going to be sort of easy to analyze? Think about loading in the 2 and the 3 directions. What's going to dominate that behavior? What's dominating the behavior if I load this? Stress concentration. Yeah. Stress concentration, right? We got a bunch of like circles in there. Yeah. Stress concentration. Okay. So easy to analyze because stress concentration. So basically stress concentrations are just going to dominate this. You're going to fail in the matrix right on the outside of the fibers, right? The two that are really hard: longitudinal tension, longitudinal compression. Those are really hard. And we'll get into why that is momentarily. Transverse shear, medium difficulty. Okay. All right, so let's get into it. Before we really talk about any of these specific directions, let's just talk about like how composites just kind of fail in general. All right, so what you might anticipate seeing if you start loading a composite to failure. What's it actually going to like look like physically? All right, so let's talk about some actual failure modes. And this is like how this physically fails, like what could possibly happen. One mode might be just a fiber failure. Okay, there's some pictures in the notes here. I'm just going to bring those in. Maybe you want to try to do your best to sketch this. I don't know. Here's a fiber failure, or kind of a picture from your book. So this is going to be just you loaded up this thing and the fiber couldn't take it anymore. Can't take it. So pretty self-explanatory here. Fiber fails in tension or compression under the global load. I don't think it really requires any additional explanation. All right. Similarly, you could have matrix failure. And matrix failure is a little bit interesting, and that you usually see like cracks occurring inside the matrix. And then once you kind of see one, it'll start like propagating to a lot of other parts of the matrix, because like you can't hold the load here, so it has to redistribute to somewhere else, and then it can't hold somewhere else. And it's just kind of like this cascading kind of like failure mode. It's really kind of interesting. And so we're kind of sort of showing that here with these sort of cracks that are occurring in the matrix between fibers. All right, you might see interfacial failure. Sometimes called fiber pullout, for I guess pretty obvious reasons. But it's more or less a debonding between sort of the fiber and the matrix. And the picture kind of looking like this. Okay, so kind of a crack is forming around the fiber as it's sort of like losing its interfacial bond with the matrix. And the last one that you might see that we're specifically going to talk about for unidirectional composites is shear yielding in the matrix. This really tends to happen with like thermoplastic materials more than thermoset materials. And that's because thermoplastic materials can have sort of like a yielding behavior. So common for thermoplastics. Or just any general ductile matrix phase. Oh no, that did not work. And so there's kind of your picture. And what they're trying to show in this picture, it's not entirely clear, is that you have like failure here in the sort of in the matrix. It's like this 45-degree shear bands that are occurring. And that's happening just because that matrix around that stress concentration or hole or whatever is there is sort of beginning to yield. And so it's not really holding load or carrying load anymore. And you're going to get some elongation in that region and things are bad, right? Here, I've only really discussed what are like unidirectional composite failures. We are not yet talking about failures of stacked unidirectional layers. So things like delamination, not yet. That's not yet. That is another type of failure, but not something we're going to really talk about quite yet. All right. So just kind of physically, you're going to see failures that are just different than what you might see from traditional materials, just because you have like two materials in one, right? A composite, physically distinct materials. So you could have failure of component A, you could have failure of component B, you could have failure of the interface between those two things. And it's sort of unique to composites in the way that they're going to sort of fail relative to what you might think about failure for just general isotropic materials. Okay, so let's talk about our first micromechanical model, and that's going to be sort of this longitudinal tensile failure. Okay, so first mode. And we're going to start with the most complicated, because that's what we do, rawr. So this is tension of composite in the one direction. No musical jokes, please. So let's define some vocabulary that we're going to use to make our equations go here. We'll say that the strength of a single fiber in tension is given by the variable capital F sub F for fiber, one direction in tension. So capital F for failure, you guys are all familiar with that. Subscript little f for fiber, one direction in tension, right? Remember, because our fibers can be anisotropic as well. Right? Let's do the strength of matrix. We're going to assume isotropic matrix. It's just capital FM. And let's just put a T on there because we're going to remind ourselves that we're sort of in tension here. But most of the time, a matrix has similar failure in tension and compression, but we'll keep the T just for now. All right. So now let's get into our model. We're going to make some assumptions here that are similar to the assumptions we made when we looked at the stiffness in the one direction. So here we're going to assume some similar assumptions we made for the strength, or sorry, the stiffness development. We have uniform fiber strength. Okay, so the strength is the same along the entire length of the fiber. We have a perfect bond between matrix and interface. And here we're going to assume isostrain, same thing that we did when we developed the stiffness. That means the strain in the one direction of the composite is the strain in the one direction of the fiber, and it's the same as the strain in the one direction matrix. Okay. So to sort of develop our model, we're just going to apply load in the one direction and see what happens. So apply load in one direction. And we're going to have something like the load in the one direction is equal to the load that's on the fibers plus the load that's on the matrix. Right? So the sort of model that you should have in your head kind of this like single fiber model, like normal. And we're just pulling this guy sort of entirely in this direction with P. And so we're splitting the load between the fibers and the matrix. And so the load in the one direction of the composite is split between the load that's on the fiber and the load that's on the matrix. All right. Obviously, this is like 1, 2, 3. All right. Okay, stress. Here's going to be stress in the one direction of the composite, stress on the fiber, volume fraction on the fiber, plus stress on the matrix, volume fraction on the matrix. I think that sort of just comes relatively simply from sort of what we've written above. Could divide all of these things by their relative areas, and we know the volume fractions accordingly. So you would be tempted to write the following. Just like you did for the development of the stiffness, you might want to write that the strength in the one direction of the composite in tension, it's F1T, is equal to the strength of the fiber in the one direction in tension times the volume fraction of the fibers plus the strength of the matrix in tension times the volume fraction of the matrix. It seems like a very standard procedure, right? This is not correct. Oh my God, is this not correct? Okay. The strength of the composite is not the sum of the strength of the individual components multiplied by the relative fractions. That is not going to happen. And that's because the materials do not fail at the same time. One is going to fail before the other. And so the combination of the two components' strengths added together is not really what's going to happen in reality. Either the fibers are going to fail first, and that means basically your composite has failed, or the matrix is going to fail first. And again, your composite has failed. So the question is, when is that failure going to occur, and how do we determine what the stress is in the composite when one of the first two constituents fails? That's what we have to determine. So let's put this into words. So fibers and matrix do not fail, or let's say do not reach their failure strengths simultaneously. I think that's a little bit more clear. Let's say that. They do not meet their respective failure strengths at the same strain. Okay, they have different strains to failure. Rawr! Okay, I say this every year. It's not the sum of the strengths of the individual components in the one direction. But I promise you someone on their test will do it. It happens every time I teach the class. All right? This is not the right way. This is not the method. Okay? They have different strains to failure. So we want to determine, given our composite, what's going to fail. We have to find out which one of the constituents has a lower strain to failure, assume that they all have the same strain when we load them, and then calculate what the stress is on the composite when we reach that lower component's strain to failure. That's the method. Got it? You got it? Do you got it? All right. Jack. Jack asks, is our isostrain assumption good or bad? In this condition, isostrain in the one direction is quite good. The isostress in the two direction, not so good. And that's because of stress concentrations, right? So isostress assumption when we have like the series model, not very good. But isostrain assumption when we have the parallel model is actually very close to reality. Cool? All right. So we have to deal with this. So let's look at kind of what these conditions might be. And the first would be, what happens if our fiber has a lower strain to failure than the matrix? So we'll call this case 1. And the strain to failure we'll call epsilon F1T. Strain to failure of the fiber in the one direction in tension is less than matrix strain to failure, which we typically will call EMT. And by E, I mean epsilon. Vocabulary, people. All right. So in math language, we would write that the strain to failure of the matrix in tension is greater than the strain to failure of the fibers in tension in the one direction. All right, something like that. This is how we would write it in math speak, because we're engineers and we speak math. All right. So here, if we're assuming isostrain in the one direction, the fibers will fail first. That's sort of pretty obvious. Okay. So here we'll say fibers more brittle than matrix. Okay. As you load, the material is going to strain in the one direction. Okay. And then the assumption that we make here is that right when we reach the strain to failure for the fibers, all of the fibers fail at the same time. That's not really what happens in reality, but that's the assumption that we have here because all fibers are carrying the same stress. That's what we said in our assumptions. Okay. And then once strain reaches strain in the fiber in the one direction in tension, all fibers fail. We know that that's really not what happens in practice, but that's what we're gonna assume. So then fibers no longer carry load. At that point, one of two things can happen. Either the matrix, once the fibers have stopped carrying the load, can still hold together what load remains, or the matrix might fail as well, and we have to determine that. At very low volume fractions, imagine you have one fiber in a giant massive matrix. Okay, if that one fiber fails, you're probably still fine. Okay, so at low volume fractions, you're probably okay. But if you have tons and tons and tons of fibers, basically, let's say 70% fiber volume fraction, and then all of a sudden they all fail once you reach this fiber strain to failure, then there's no way that that 30% matrix that's left over is probably going to be able to hold that load, and the whole thing is just going to like catastrophically fail. Okay? So let's put some math to that. Okay? So right before fibers fail, stress is whatever stress, well, right before it fails, it's the failure strength of the fiber in the one direction in tension. It's right on the cusp of failing. So the fibers are holding just about the amount of stress that they would take before they fail, multiplied by the volume fraction of the fibers, plus the volume fraction of the matrix, multiplied by some intermediate strength of the matrix we're going to call here FMT prime. All right, so let's actually look at what this value is. And let's look graphically at what's going on here. All right. So what we're going to graph here on this sort of pseudo axis is the strain versus the stress. So your stress strain diagram. In the situation where the, fibers are going to fail first, typically the fibers are stiffer. So let's look at sort of the stiffness of the fibers. You're loading, you're loading, you're loading, and then ultimately they fail. So this is just sort of considering the fiber component. We're not really talking about the composite yet, just the fibers. That failure strength through the fibers is going to be F1T of the fiber, right? Or FF1T, I think it's kind of what we were going with, right? Set failure value. If you just had matrix material, the matrix typically is less stiff. And we're saying here that the matrix has a larger strain to failure in this case. So if you just tested matrix material, you would have something that looks like this. Here, this value would be the strength of the matrix in tension. Now our composite is going to have a stiffness that's a combination of both the matrix and the fiber. Okay, so the stiffness is going to be somewhere between that of the fibers and the matrix. And we know that the composite will fail when the fibers fail. Okay, so we're going to have a little bit higher stiffness. And we know that the composite fails when the fibers fail. This value here is F1T. It's the strength of the composite in tension. We can give some sort of strain values here that are important. This is the strain of the fiber in the one direction in tension that would cause failure. This here is the strain in the matrix in tension that would cause failure. Okay, so here's my point. The stress that's in the material right when the fibers fail, what is that value? All right, well, it's a combination of whatever the fibers are holding right before failure, and we know that that's going to be the failure strength of the fibers multiplied by their volume fraction, plus the amount of strength that we have in the matrix at the strain of failure, okay? So the amount of strength or the amount of stress that's being carried by the matrix at the point of failure is going to be this value here. This is our intermediate value, FMT prime. You have to think of FMT prime as the amount of stress that the matrix is carrying when the fibers fail. Okay. That value is going to be equal to the modulus of the matrix multiplied by the strain to failure in the one direction in tension of the fibers. Got that? So this is an important value here. All right. So right before failure, this is our stress. All right. Okay. So right before failure, that's our stress value. Okay. Now, like I said, we could have two possibilities. When the fibers fail, our matrix could be strong enough to still retain the amount of load that was lost from the fibers, and we still could have our composite intact. Or the matrix might not be strong enough to hold whatever load was transferred from the fibers to the matrix, and it could just fail catastrophically. Okay, so after fiber failure, the stress on the composite is the following: 0 plus, let's just say, the stress that's in the matrix in tension times the volume fraction of the matrix. Our fibers failed. They are no longer carrying any stress. So whatever left on the composite after that is entirely held by the matrix. All right. We have two possible outcomes, as I mentioned. If the volume fraction is high, in this situation, the load that's transferred from the fibers to the matrix can't hold it. It's too much. I can't stand it. All right. It's too much. Can't hold it. Okay. In this case, the material will fail catastrophically. All the fibers fail. The matrix can't handle it. Bang, the matrix fails. Right. So what that means is the stress that was on the composite right before the matrix fails is then the stress of the matrix, the stress that would cause failure in the matrix multiplied by the volume fraction of the matrix. So let's put that in math language. The strength of the fiber in the one direction in tension multiplied by the volume fraction of the fibers plus this amount of load that was carried by the matrix in tension multiplied by the volume fraction of the matrix is greater than the strength of the matrix in tension multiplied by the volume fraction of the matrix. This here is what the stress is on the composite right before fiber failure. So that's basically the stress that's going to be on the composite right after fiber failure, but we no longer have fibers to hold the load. So right before fiber failure, that's our value. If that's greater than the stress that would cause failure only in the matrix, then we fail. All right. So in that situation, this would be the governing strength of that composite. So in that situation, the strength of the fiber in the one direction in tension, the strength of the composite in the one direction in tension is just equal to this strength of the fiber in the one direction in tension multiplied by the volume fraction of the fibers plus FMT prime VM. Where this FMT prime is the modulus of the matrix multiplied by the strain to failure in the one direction of the fibers in tension. Complicated. Dang. So that's if we have very high VF. The other case, low volume fractions. In the case of low volume fractions, the amount of load that's actually being held by the fiber right when the fiber fails is very low. Okay, so imagine the situation where you have one fiber in a huge matrix, right? You load this thing up, you're going to strain that fiber where the fiber is going to fail. It's going to transfer its load to the matrix, but the matrix is like, did you guys feel something? Like, what's going on? Did you feel that? Did that fiber just? Oh, I didn't even notice. Okay. So the load carried by fibers transfers to matrix, and the matrix can stand it. The matrix can hold it. Okay. So in that situation, the stress that's on the composite right before failure is less than kind of this strength of the matrix times volume fraction of the matrix. So here, mathematically, that is the strength of the fibers in the one direction in tension multiplied by the volume fraction of the fibers added to this strange FMT prime term times volume fraction of the matrix. This is less than that which would cause failure if it was just on the matrix. That's failure of the matrix in tension times volume fraction of the matrix. So in this situation, this is going to govern the failure because, okay, the composite's loaded, the fiber fails, but the matrix is like, whatever, I'm good. And so then you just load up and now you're just loading matrix material. And so now you just go until the matrix fails, right? Okay, so then the strength of the composite in the one direction in tension is just the strength of the matrix in tension times the volume fraction of the matrix. Okay. We'll stop it here. It's about 4:50, so we'll call it. Thanks for coming. See you on Monday. Look for the new homework. I'm going to post a new homework on thin laminates, sort of the stuff we talked about last week, or I guess earlier this week. Lucas asks, is there specific values where one might classify VF as low? We're going to talk about that next time. What do we consider high, low VFs? We'll talk about that. You can actually analytically solve for it, and we'll show you how next time.